All right, we're going to do a little bit of AP review. So, this video is about the 2012 AP, AB, and BC free response 1. So, it's the same free response for both AB and BC. So, hopefully you have this problem in front of you if you're watching this video, because I'm not going to recreate all of the diagrams that were given, but I will read you the problem. The temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where w of t is measured in degrees Fahrenheit. Where w is measured in degrees Fahrenheit and t is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes, beginning at time t equals 0. Values of w of t are selected at selected times t for the first 20 minutes are given in a table. So they give you time 0, 4 minutes, 9 minutes, 15 minutes, and 20 minutes, and they give you the temperatures at those times. Part A says, use the data in the table to estimate W prime of 12. Show the computations that lead to your answer. Using correct units, interpret the meaning of your answer. So the trick is that they ask us to approximate W prime, right? So remember that in the most basic of ways, derivative essentially means slope, right? A derivative is a rate of change or a slope. So W prime of 12 is essentially going to be approximately the old school slope of points around 12. So since on the table I'm given times 0, 4, 9, 15, and 20, to approximate 12, I want to use W of 15, which is a given quantity on the table, minus W of 9 over 15 minus 9. So on the table, I'm given that this is a 67.9 minus a 61.8 over a 6. This is a calculator section on the AP, so I'm able to go ahead and say that W prime of t is approximately 1.017 or 6, depending on if you round or truncate, degrees Fahrenheit. Because W is measured in degrees Fahrenheit and t is measured in minutes, right? This would be degrees Fahrenheit per minute, right? So when we're asked to give appropriate units, and then we're also asked to explain the significance of this measurement. So what this means is that at 12 minutes, the temperature is increasing at approximately a rate of 1.017 degrees Fahrenheit per minute. So again, at t equals 12 minutes, the temperature is increasing at about 1.017 or 6, again, degrees Fahrenheit per minute. Okay? All right, so that's our part A. Now, rather than leave that there, I'm going to erase it so that we have room to see what part B would be, because it's a video, so you can go back if you need it. All right, part B says, use the data in the table to evaluate the integral from 0 to 20 of W prime of t dt. Using correct units, interpret the meaning of the integral from 0 to 20 of W prime of t dt in the context of this problem. So in part B, I'm asked to integrate from 0 to 20 of W prime of t dt. Now, it is worth noting that I was not asked to approximate it this time. I was asked to evaluate it, meaning I should get the actual answer. So the first fundamental theorem of calculus tells us that if we integrate a derivative, we essentially just get the original function, so W of 20 minus W of 0. Well, those are both values that are given on our table. So on our table, we get that that is a 71 degrees minus a 55 degrees, right? And both of those measurements are in degrees Fahrenheit. So what's going to end up happening is I get this is 16 degrees Fahrenheit. Well, W of 20 is the temp at 20 minutes, and W of 0 is the temperature at the start of the problem. So essentially what this is saying is there is a net change of 16 degrees in the first 20 minutes. So the temperature has warmed, right, warmed or increased, right, by 16 degrees Fahrenheit in the time from t equals 0 to t equals 20 minutes. When you're asked about something like this, you should make sure that you state the time period that they're talking about, because the integral goes from 0 to 20, so it's important that in your explanation you include the time interval you're talking about. So again, the temp has increased by 16 degrees Fahrenheit in that time period. All right, let's talk about C. Part C. for the window from 0 is less than or equal to T is less than or equal to 20, the average temperature of the water in the tub is 1 over 20 times the integral from 0 to 20 of W of T dt. Use a left Riemann sum with 4 subintervals indicated by the data in the table to approximate 1 over 20, the integral from 0 to 20 of Wt dt. What does this approximation over or underestimate the average temperature of the water in those 20 minutes? Explain your reasoning. All right, so we're asked to use a left Riemann sum, right? So a left Riemann sum means that you're going to use the left y value as the height for the box. Remember that the height of each box is the change in, usually it's x, in this case it's t. So in part C, the first thing I'm asked to do is take this value, the integral from 0 to 20 of Wt dt, right, and put a 1 over 20 in front of it because that's the average value formula. So I'm going to approximate that with a left Riemann sum. So I'm going to put the 1 over 20 at the front, and then when I do my left Riemann sum, the width of the first box goes from 0 to 4, so the width of the box is 4, right, and then of the two y values, the left one is the 55, right, plus the next interval goes from 4 to 9, which is a width of 5, and the left y value is a 57.1 degrees. The next value, and I'm actually going to probably end up looping down below this just because I want you to be able to see it on the screen. The next window is from 9 to 15, which is a width of 6, and the left of the two y values is the 61.8, right? And then the last window goes from 15 to 20, which is a width of 5, and the left of the two y values is the 67.9, meaning I never use the rightmost value, which is the 71 degrees. So you want to make sure that you show all of this work. You want to show this setup, right? Because one of the points you're probably getting is for showing that you know what a left Riemann sum is. It is a calculator section, so you're able to type all of that in a calculator, but you need to make sure that you show that work so you get credit for your left Riemann sum. However you choose to do it, I think a lot of us are going to clean up this number first and then divide the whole answer by 20. Certainly if you do that, that's what the AP does. They get, this is a 1215.8, and then they times it by the 1 over 20, and they get that that approximate answer is a 60.79. Again, make sure that we put the correct units, right? It's degrees Fahrenheit because this is the average value of the W of T dt, right? They ask us if this is an under or over approximation. So here it's important that we note that they went out of their way in the original introduction to the problem to say that this is a strictly increasing function. So just to show you what we mean by that, if we have a function that's increasing, so this is a random fake graph, let's pretend this is my W of T. If my function is increasing, right, then the left endpoint will always physically be below the right endpoint, right? The one on each interval, the left one, will be lower than the right one because a strictly increasing function means that lower x values come with lower y values. So essentially what we're finding here is that the left value is always physically going to be shorter than the actual curve, right? And again, I just used a linear curve here, which is obviously a very oversimplified example. But the idea is that if my curve is strictly increasing, my left endpoint will always be smaller than the actual value of the curve, so it should be an underestimate, right? And they ask us to say why it's an underestimate, so the answer is it's an underestimate. They'll never give you the credit. On a 50-50 answer, they'll never give you the credit for the answer without the explanation because they're not going to give you the chance to get a point for just a yes or a no or an under or an over. So it's an underestimate because W of T is strictly increasing. You can just quote what they told you. It's strictly increasing, right? And what that means is that the left endpoint is smaller than the right end, right? So you could probably get away with just mentioning that it's because it's strictly increasing. That's the piece of information that they need. All right, let's talk about part D, and then we will end this video and do another problem. All right, so part D, sorry, my paper's inching over. Part D says, for 20 to 25, so for T is 20 to 25, the function W that models the water temperature has a first derivative given by W prime of T equals 0.4 square root of T cosine of 0.06 T. Based on that model, what will the temperature of the water be at 25? So here, this is one of those times that they're tricky because they're essentially giving you a whole different problem that uses very little of the original information. So here's the idea. So in part D, we know that we could integrate from 20 to 25 of W prime of T dt because this is an equation that we can put in our calculator, right? So in our calculator, we're going to put in y1 equals 0.4 square root of x cosine of 0.06x. Now, you're going to make sure your mode is radian, as always, right? There's never a time in calc that we ever want to be in degree mode, right? So your mode's going to be in radian. And this is stuff that you don't need to tell the AP, but that you need to know how to do, right? So you're going to put that in. And we know from the first fundamental theorem of calculus that if we integrate from 20 to 25 of w prime of t, we should get w of 25, which is the answer that we want, right, minus w of 20, which was given on the table, right? This was given on the table to be a 71 degrees Fahrenheit. So I'm pretty sure that if what I type into my calculator is 71, so I'm going to add that 71 over, plus the integral from 20 to 25 of 0.4 root t cosine of 0.06 t dt, that I'm going to get w of 25. So you just need to convey this information, right? So this is what the AP needs. The AP needs to see this, and then the AP needs to see a mathematical answer. And when you type this in your calculator, you're going to get 73.043 degrees Fahrenheit as your W of 25. And that's what they need to see. Just a reminder of how you type this into your calculator. So right here, once you call that y1, you're going to type in function integrate, which is math 9, right? So it's math and then 9, parentheses y1, which you get by going to vars and then picking y vars, and then picking function and 1, comma, with respect to x, from 20 to 25. And that's how you're going to enter this piece into your calculator. To that, you'll add a 71, and that's when you get the 73.043 degrees Fahrenheit.